Here regarding tomorrow's Quiz 2 activity. I suggest you take a look at the solution keys to these two questions. Of course, available on Sakai. As you recognize, the quiz is really two parts. Multiple choice to keep with the exam format, and then the other part of the quizzes, which is the type of question stuff I prefer, where you are invited to explain yourself so that we have a chance to find out what you in fact know. We know nothing of the kind when all you do is mark an answer. Who knows? Maybe it was just your lucky day and you marked the right answer by good fortune. We hope that's not the case, but unless you come to see us and demonstrate that you can work the problem in our presence, we don't know. In any case, the so-called white space question, or as I believe students have a habit of referring to such, free response, whatever you want to call it. On tomorrow's quiz, we'll parallel this stuff, and we'll invite you, of course, to demonstrate in regard to equilibria which contain salts of limited solubility, your knowledge of water solution acid-base chemistry on such. Water solution acid-base chemistry. How many viable forms are there of this stuff in water solution? I'll give you a clue. They're all written in the acid-base table. Not the one that's in the notes, but the one I told you to copy from the website. The lecture website, the internet website. If I add H plus to this, do I have a viable form of phosphate-containing stuff? Yes. If I had 2 H pluses? Yes. If I had 3 H pluses? Yes. Do you think these various forms and their existence have a strong dependence on pH? Absolutely. Now then, we proceed with our analysis of systems of semi-soluble salts prepared by saturating the salt in a solution which is more acidic than water, with the stipulation being that none of the component ions of this solution, which is more acidic than water, functions as a precipitator of the salt. We looked, for example, at that last time on considering the solubility of calcium sulfate and sodium hydrogen sulfate solution. You could do the same for the solubility of calcium sulfate in sulfuric acid solution, which I would hope you would begin by recognizing, since in laboratory you prepared calcium sulfate by adding calcium in the sulfuric acid solution. That calcium sulfate is not particularly soluble in sulfuric acid solution, even though sulfuric acid solution is pretty damned acidic. Because hydrogen sulfate ion, a principal species of sulfuric acid solution, is a precipitator of calcium sulfate. But now we look at the case of calcium carbonate and its solubility in ammonium chloride solution, where neither ammonium ion nor chloride ion is a precipitator of calcium carbonate. But ammonium ion is a stronger acid than water. Upshot, whatever the solubility is of calcium carbonate in ammonium chloride solution, it's got to be bigger than the water solubility, straight water solubility of calcium carbonate, which you may recall from a data point standpoint is 1.4 times 10 to the minus 4 molar. That's the experimentally determined Normal laboratory condition, water solubility of calcium carbonate. So whatever the solubility is of calcium carbonate in the ammonium chloride solution, it's got to be bigger than 1.4 times 10 to minus 4 molar. That's the information we have when we start this problem. Always keep aware of what you know. All right, last time we recognized. This is the main equilibrium established in this system. Here's the K expression. Here's how we have to treat the K expression to evaluate K. And find out the K expression is when I multiply by hydroxide ion over hydroxide ion molarity, I get this. Last time I believe we showed that if I multiply this by hydronium ion over hydronium ion, I can still evaluate this. Doesn't make any difference, won't change the value. I put in the numbers for these Ks, all of which are available in our acid-base table, or information sheet, I should say, not acid-base table, because this is KSP. And this, of course, comes from Ka for the conjugate acid of carbonate ion, which is HCO3 minus. And when you look at this number is already telling you that calcium carbonate is more soluble in this system than it is in straight water. You believe that? In your mind's eye, since we've done a lot of work with this, calcium carbonate plus water, double arrows, calcium ion, bicarb ion, hydroxide ion. You remember the K value? 1.3 times 10 to minus 12. Does that ring a bell? 1.3 times 10 to minus 12 is a smaller number than this, which means from an extent standpoint, this goes further as written before equilibrium is achieved. Which means you put more calcium ion, you put calcium ion in solution at a higher molarity by establishing this equilibrium. Which means calcium carbonate is more soluble in this system. We've already proved it. Now let's be a little bit more detailed in our proof and get some solubility information as well as pH information. We begin by asking the question, for this system, is it reasonable to take the equilibrium molarities of calcium ion, bicarb ion, and ammonia to be about the same? Now we know the calcium ion molarity is the same as S, solubility. So is S the same as these? For this system? Well, what we're really asking is, A, is it reasonable to believe for this system that the principal carbonate-containing species by far is bicarb ion, as opposed to, or in addition to, carbonate ion and hydrated CO2? All right, let's talk about that. Calcium carbonate in water. Do you recall that in that system, carbonate hydrolyzes 70%? And we've already established that in this system, carbonate hydrolyzes. Well, it doesn't hydrolyzes, it ammoniumizes, ammonium ionizes. Have we not verified that in this system, calcium carbonate reacts to a larger extent with ammonium ion and calcium carbonate reacts with water? Isn't the K value bigger here? We just talked about that. See, what I'm doing is to continue to try to make an effort to get you to understand what this stuff means, because that's where it's at. When this stuff talks to you, you're understanding the chemistry. That's the hard part. I'm very sympathetic with you, but that's the part that matters. Well, we know carbonate is reacting to a considerably larger extent in this system than it is in water, where it goes 70%. So that suggests that carbonate is not a principal carbonate-containing species in the pot. Well, the only other possible form is H2CO3. Well, let's take a peek at that. Oh, pardon me, before we take a peek at that, let's recognize that whereas water plus carbonate ion is a small extent acid-base reaction, this is a large extent acid-base reaction. You know how to play the extent game. You get out the acid-base table, you see that this is a stronger acid than this, and this is a stronger base than this. The extent is large. In fact, now you know how to calculate the K for this. If you do it, you'll get 10. That's the value. So this is a large extent reaction. Again, supporting the conclusion that of the possible forms of carbonate in this system, carbonate is not going to be one of them. Now, what about H2CO3, hydrated CO2? Well, the only source of consequence of hydrated CO2 in this system will be this reaction. Now, do we expect this reaction to stand a better chance of making this than water reacting with this? Hell yes, because this is a stronger acid than water. But this is a small extent reaction. You can calculate K for this. You'll find out it's a small number. So that suggests that the only species of consequence carbonate-containing stuff is bicarbonate, which is what this is based on. But there's another issue here. What's the other issue? The other issue is it possible that in this system, where I've written, is this reaction negligible in this system? Do you remember reading about the gang-up factor? It's in the notes. Your job is to read the notes. What's the gang-up factor? How does the gang-up factor relate to this system? Even though ammonium ion plus bicarb ion is a small extent reaction, is it imaginable for this system that we do develop a measurable molarity of hydrated CO2 because ammonium ion gangs up on bicarb ion? What does that mean? Ammonium ion gangs up on bicarb ion. Well, I'll tell you a story. I like stories. I'm not much for this pugilism game, but I did rather enjoy watching Muhammad Ali. How many of you remember Muhammad Ali? He was rather poetic in the ring. And I shouldn't display my bias, but when he did in certain other fighters who, in my opinion, were oafs at best, I enjoyed it. When Muhammad Ali was in his prime, he was unquestionably the best fighter at that time in the world. What chance would any of us have stood had we gotten in the ring with Muhammad Ali and went like this here? No chance. But if the whole damn bunch of us went in there and started wailing away, maybe 40, 50, 60 of us would lose our lives in this process, but eventually we would gang up on him, probably, and do him in. Maybe. That's the gang up factor. And I put the, maybe. Maybe if the enrollment was another 200, and we'd have a better chance. And we'd gang up about 300 to 1. Oh! Oh! That's a gang-up factor. So I repeat, is it imaginable in this system that due to the gang-up factor regarding ammonium ion and bicarb ion, that this reaction will go to a measurable extent and so produce a measurable molarity of hydrated CO2? You recognize that the initial molarity of ammonium ion in the system is 1? What kind of a molarity are we going to have for bicarb ion? Not much. The only possible source of bicarb ion is calcium carbonate, and we know that calcium carbonate, even though it's more soluble in this system than it is in water, when I get this K value, 7.2 times 10 to the minus 8, do I think calcium carbonate's pretty soluble in this system? Do you have reason to believe by experimental knowledge that you should have that calcium carbonate is not particularly soluble in ammonium ion? Back to 46 laboratory, which by now most of you should have experienced. Specifically, one of the investigations you were asked to make in 46 laboratory is to take calcium chloride solution and treat it with quote-unquote ammonium carbonate solution. How many of you did this? What happened when you did this? You did it? You don't remember what happened? What's going on here? You in the laboratory like this? Don't pay attention to what you're doing? Are you going through the laboratory by taking advantage of information from somebody's lab manual that's been completed at a previous term? I can't stop you from getting your hands on that stuff. But if the lab instructors do their job, it won't matter whether or not you have that stuff at all. Because they will insist that you do the work that's called for, and they will insist on questioning you about it until you demonstrate that you understand it. And if you understand it, I don't give a damn if you learned it because you looked at somebody else's information. What counts is that you learned it. That's what I want. I want you to learn. That's what the heck you're here for. It's the people who don't learn, or worse yet, don't want to learn, but want to get a grade. Those are the ones I'm after. They'll kick their butts out of here so fast their heads will spin. They don't give a damn how much tuition money you got. I don't care how powerful your parents are. If you're here for a purpose other than learning, I'm going to do what I can to run you off. You don't belong here. You got that? You know that about me. I don't see any more wonderful endeavor in which humans can engage in than learning. That's where it's at. In any case, back to chemistry. We'll get back to the sermon when appropriate. Because of the gang-up factor, this might go. Now, we also have to answer the question, since part of this consideration is the likely relationship between S, calcium ion, and ammonium molarity, is there any other possible source of ammonia beside this reaction? Well, this is a possible source of ammonia. If this goes measurably, then it's also going to contribute measurably to the ammonium molarity. In addition to this, and in addition to that, is there still another possible source of ammonia in this system? Are you rolling about in your mind's eye the principal system inventory? Ha ha! You better always do that. That's it. That's where it's at. Pay attention to what you got, what you're dealing with. What, if any, is another possible source of ammonia in this system? If I take the ammonium chloride solution all by itself, forget the calcium carbonate, is there going to be a measurable molarity of ammonia in there? Where's the ammonia come from?
Acid-base reaction.
Comes from what?
Acid-base reaction.
The acid-base reaction of?
Water.
Ammonium ion and? Good. That's the other possible source. So that might also contribute to the ammonium molarity. These are things we want to keep in mind. Now let's get on with this. Believing at this point that the only source of ammonia of consequence is that reaction, and the only source of bicarb ion is that reaction. That keeps with this. So I write this. Algebraically it becomes this. I solve it for S, and I ask at this point, does it seem like a reasonable result? Well, it's not a big number. And this K value has told us that whatever the solubility is of calcium carbonate in the ammonium chloride solution is not going to be large. But does that number correspond to a solubility of calcium carbonate which exceeds the solubility of calcium carbonate in water? Let's put that value down again. S DIW is this? Well, hey. Hey, this is bigger than this. Appreciably bigger. So it looks like we're in the ball game. All right? Now then, how would we find out if this solubility value is correct? Is it reasonable? Well, we've talked about it being reasonable. Well, we'll find out if it's right on the nose. We got a good idea we're in the ball game. Is it right on the nose, the 2 sig figs? How are we going to find out? We got 2 ways. The second way we're going to pursue on Wednesday, right here, by experiment. We're going to make ammonium, 1 molar ammonium chloride, and saturate it with calcium carbonate, and we're going to get a pH meter, standardize the pH meter, and measure the solution pH. And see if it keeps with the calculated solution pH for this system that we get from that solubility value. That's the experimental check. Now the other check is a check that you already know how to perform. It's the detailed, rigorous analysis of this system, which means beside the equilibrium considerations on the board, what else would we apply? What else? Charge balance and material balance. Because that analysis considers everything. That analysis, if we don't mess up the arithmetic, will be correct. That we'll pursue further in a moment. But let's get at this pH issue. Based on this solubility, based on this solution, to get this solubility, how for this system will we calculate the corresponding pH value? There's 2 ways to do it. Any suggestions? And the data we need is on the board. Any suggestions? Calculate the system pH. 2 ways.
Use Kb of carbonate.
Kb carbonate is one way. There's a simpler way. What is it? That's the same thing as Kb carbonate. Aren't there 2 species in this system? Different species whose existence depends on pH? Ammonia, ammoniumine? You betcha. So let's take a look at Ka ammoniumine. We could use Kb ammonia, but I want pH, which means I want hydronium ion concentration, so I'll go straight away for hydronium ion concentration by looking at this. This is what we want. What's this? Based on what we've done. What is it? There it is. Isn't it? What's this? Based on what we've done. I hope all this stuff looks imminently obvious. We've done this many times. We're just doing it again. Okay? This gives me I think it's 1.3 times 10 to minus about. I better take a look because sometimes I mess up the memory part. No, that's it. telling us, based on this, that the solution is very mildly acidic. This corresponds to a pH of 6.89. Yeah. So what we're going to do next time, as I said, is make saturated calcium carbonate in 1 molar ammonium chloride, make that system, and observe the pH. With a pH meter that's been standardized. And see if we get this value.
Why would it have been harder to use Kb carbonate? Why is it different than what we just did?
Well, if I'm going to use Kb carbonate,
Or Ka?
Ka bicarb, let's take a look. Maybe I misspoke. Now, okay so far? Here's what we want. This is 4.2 times 10 to minus 3. What's this? We didn't report a value for this one yet, did we? So we have to do more arithmetic to work with this. That's why this is more direct. Because here we only got one unknown, based on the work we've done so far.
Is that we don't know HCO, the concentration in the bottom one, because there might be bicarb.
Well, I mean, where have we reported the carbonate ion molarity so far?
Wouldn't it just be 1 minus carbonate?
Don't forget, we've established that this is likely a species that's in there at measurable molarity. So you got some problems to wrestle with if you want to play with this. But you can do it. On the basis of what we have, you can do it. But we've demonstrated this is ready to go. So I use this. Okay? Now then, we told you what we're going to do to go further with this. We're going to do the experiment next time, see what kind of pH value we get. Now, while I clean up and prepare for the next part of this analysis, let me remind you about a pH meter. Well, let me ask you a question. Do you think a pH meter measures hydronium ion molarity and reports it as a pH? Or do you think a pH meter measures hydronium ion activity and reports it as a pH? Measures activity. It can't do anything but. You know, the meter is sensing how many hydronium ions are swimming around in the system behaving as individual particles. That's what activity is based on. And in this system, we have a high ionic strength, do we not? At the minimum, we lace the pot with ammonium ion and chloride ion. And those species, because they're present at high ionic strength, may well affect the activity of hydronium ion. In fact, I know they will. So if and when we do this pH meter measurement, now we got to also pay attention to some extent to activities. Makes the pot more muddy, doesn't it? But that's the fun of the game. So we'll talk further about that next time, since next time we're going to do the experiment part. Okay? Now then, let's get on with the part of this puzzle that you know how to do. The rigorous calculation. Oop. So as we go through this, why don't you work along with me? Given that on tomorrow's quiz, I will expect you to write material balance equations and charge balance equations. How's that? For a clue. What can we write material balance-wise on this, for this system? Can we write this? We can write that, can't we? And straight away, I don't see that we can write any other material balance relationship and not have it be equatable to a number. I mean, we know the possible viable forms of carbonate-containing stuff, but we don't know what value that sum of concentration terms will equal. I mean, on the basis of what we've done, we believe it would equal 4.2 times 10 to the minus 3, but that's not a rigorous calculation. This is. Okay? But we will write this. Because this is a rigorous material balance relationship. We don't know what S is. That's what we want to find out. We've shown a way to get a handle on it. We don't know yet how reliable this value is. But this we can say for sure, which is a material balance relationship. All the viable forms of carbonate-containing stuff, the sum of their molarity has got to be equal to calcium ion molarity, which is equal to S. How then? Let's write charge balance. Do it. Put it in your paper right now. Can I put any numbers in here? Yes or no? Can I put numbers in here? The hell I can.
Why isn't calcium ion part of the...
Oh! What am I doing? That's good. I get too close to my work, I mess up. There. Now, can I put some numbers in here? Where? Ha! Can I do that? See the label on the bottle? Damn right I can do that. Now, to two significant figures, you think it's legitimate to say that twice the calcium ion molarity plus the hydronium ion molarity plus the ammonium ion molarity is in fact 1.0 for this system. Well, if the solubility is sufficiently small, you bet that's legitimate. But we don't need to put that in there. We'll find out. Now then, tell me, based on what we have, can I make any simplifications? I shouldn't say based on what we have, but based on what we've thought about. How's that? Would you bet that 2 carbonates is practically nothing? We've already argued why the observable molarity of carbonate in this system is going to be damn near nothing. So we can likely eliminate that if we want to. Okay? But if I want to keep this in, and I don't want to throw it away, can I express the molarity of this in terms of something else that's on the board? Something that I want to keep in. What is that something? Bicarb? Oh, I could use bicarb, but there's a different something. I think a more straightforward way to play this game. To express the carbonate molarity in terms of something else that we already have on the board. Nope. Calcium ion. How? Oh, you just offered a vote, huh? Come on, defend the vote. That's right. I want to know how the molarity of carbonate ion is expressible in terms of the molarity of calcium ion. It's called KSP, isn't it? How about that?
How can you use KSP? You know that carbonate ion is going to react to something.
Who cares? This is a constant. This is a constant. The number for this isn't going to change. This is 6.2 times 10 to the minus 9. So the carbonate molarity is KSP divided by the calcium ion molarity. Okay? Times 2 to put it in the charge balance. Okay? Just showing you what you can do. Now, let me show you, because it's a lot more fun if you work through this. That what you'll find out for this system we got what we need on the board. Calcium ion is the hydronium ion molarity squared times 6.15 times 10 to the 8. I will have these numbers written in 3 sig figs so that when we get to the end of the arithmetic, we'll go back to the 2 sig figs to which we are allowed. This way we won't lose anything as we go along. Plus the hydronium ion times 1.3 times 10 squared. You know, right now, don't look at this and say, ah, this is horrible. You've got all the time you want to look at it. Over Kw times hydronium ion. What do you think this accounts for? What's this? Hydroxide ion. Plus 5.6 times 10 to the minus 10. At a glance, I should hope you'd realize that's Ka ammonium ion. Divided by hydronium ion, plus 5.6 times 10 to the minus 10. Minus hydronium ion. So with what we have on the board, what I have done is to write a relationship which relates the molarities of calcium ion to hydronium ion. Notice how this relationship gets right at the parts of the puzzle we're interested in. Calcium ion molarity, which is the solubility, and the hydronium ion concentration, which is directly on top of pH, right? That's why I did this. I mean, you could play this game and have relationships for bicarb, carbonate, whatever you want. But I purposely wrote this so that I get at the properties of the system in which I am principally interested. S, which is the calcium ion concentration, and system pH. Because that we're going after next time by experiment. Now, what do you think I will do at this point? Or let me put it this way. What should you do at this point to go further with this analysis? And take this to tutoring zone? Broward Hall? You can take it all those places. And my bet is they'll say, "Ah! You're in our last class. Get the hell out of here. We don't know what's going on over there." I'm going to pick a value for the hydronium ion concentration. Given that, I know for a fact from what we've done so far that whatever the hydronium ion concentration is for this system, it's going to be close to what? Close to what? 1 times 10 to the minus 7. That's what so far we've suggested that the solution is mildly acidic. Maybe there's a little error there, maybe it's mildly basic. In any case, we know we're dealing with a solution which is on the order of neutral. So I'm going to pick a value for the hydronium ion concentration. The first value I did, I'll write this down. First test. Call it a trial if you prefer. And I'm going to solve for calcium ion. And then I'm going to see if these values satisfy the other relationships which I know hold matter-of-factly. And when the other relationships are satisfied, I know I got the right hydronium ion concentration. Now, what did I ultimately get? Well, we're out of time, so we'll start next time by writing the values which we ultimately get, and we'll talk about them further. Now, keep in mind, this kind of stuff I will never give you on a quiz or exam because the arithmetic is too long. But what counts is your recognition of the system properties that you have to deal with to solve the problem. Because once you know that, then you know how to solve the problem. The solving might take some time, but knowing how to solve the problem is really where it's at.